So good morning, everybody. It's great to come together for our very first EUB2 Academia sessions. A very warm welcome to our colleagues in EUB2. This is Vicente Perez from FEPSA, and for the moment, Chair of Technical Committee. And for the next couple of hours, we'll be reflecting on new insights and technical research about our favorite construction material, bitumen. So for our first session, we couldn't have a better guest, the EUB2 member University of Antwerp, represented by Professors Wim van den Berg, Georgios Pipintakos, and Johan Blum. And as you can see on today's agenda, they are going to drive us through their last research developments, and especially focusing on sustainability assessment, aging, and new insights for the B structures of bitumen. In terms of housekeeping, I need you to tell you the following. As Anya told you, this session is going to be recorded to be shared with you after the event. This is an EUB2 members only webinar. So EUB2 competitions, law compliance, and the GDPR policy apply. You can find them both on the EUB2 intranet. We are on Teams, so please keep your please your cameras off. Please yourself mute. If you have any comments or questions, you may post them on the chat, but I would recommend not to abuse of it because it's preferable if you raise your hand and express yourself during the question and answer periods that will be available during the seminar, especially at the end. And sometimes if we have a parallel chat, it could be some kind of disturbing for the speakers, but please post any questions you may have there. And we'll try to address any posted question, and if they don't have time to answer you leave, I assume our guests will be available to get back to you directly afterwards. And I think, well, this is all on my side. I don't want to take more time. I trust you find these academia sessions interesting and useful. And now I'm rolling the ball over to Wim. Good morning, Wim. Thank you for your participation on these sessions, and the floor is yours.
Thank you very much. Good morning, dear audience, and thank you, Vicente, for the nice introduction, and Anya for the supporting efforts today. During this webinar, I will introduce the University of Antwerp roughly as an educational institute, but probably you know us more and better as a research team. So I will present next our research group, visions and resources. Afterwards, Georgios Pipintakos, a PhD student, and Professor Johan Blum will give you more insight in their specific research on aging mechanism of bitumen and the famous B structures. And it's in its international context, of course. At the end of these presentations, there is time for question and an answering session. The University of Antwerp, a nice university, is a mid-sized university in Belgium with about 20,000 regular students and many PhD students. Courses are divided over 9 different faculties, such as medicine, law, social sciences, economics. But our favorite, it is one of these faculties, is the applied engineering, consisting of 4 departments and 7 research groups. We are a rather small faculty. However, we have a high international research output and have many multidisciplinary researches ongoing, since we are close to each other. The members of our research group, EMIP, which stands for Energy and Materials in Infrastructure and Buildings, and our department, Civil Engineering Technology, collaborate a lot with the other departments and research groups of chemistry, mechanics, electronics, and their respective research groups. Our study program, I give some details, consists of 3 years bachelor and 1 master year. It is a general study with some elective courses. I listed here all courses which are more or less connected with bitumen, asphalt, and road engineering in general. We also offer PhD projects, and currently we have 9 ongoing PhDs. In order to support industry and international educational projects, we organize several courses for international incoming students and the asphalt sector. Now, let's get a more clear view on our research. So EMIP consists of 2 sections. The BEAST section, dealing with buildings and LCA methodology, and our section, the Road Engineering Research Group. Within this EMIP structure, we have, besides several collaborative projects, also good relations with other research groups in and outside our university. For the link with industry, we have many collaborations with industrial partners and road managers, as you know. Okay, so I always start my first lecture for the students with stating that the road is of social and economic importance. Also, my colleagues know that. Our society and its development level is highly supported by the quality and reliability, it's important, the reliability of road infrastructure. And it is our mission from our research group, also as an engineer, to support this innovation so we can challenge current and future challenges and maintain this level on a high level. Our responsibility is to step outside the idea that only recycling is sufficient. And this will be on 2 aspects. What to do with the historical, still accumulating pavement assets, and secondly, making the right decisions right now, today, for the challenges in future, optimizing its future use. So currently, if you see the positive side, we have sufficient potential resources, as you know, like asphalt. But on a negative way, the decisions in the past were not done with a future view on reusing these assets. So we have some problems now. So we have a double task as engineers next decades. Both society as industry expects better results and more answers from us, from our research group and our industry. So our strategic vision on sustainability is to go beyond current actions and methods such as carbon footprint, recycling, service life, biobinders, by detecting future challenges and what is needed to be ready for future. So we want reliable and future-proof infrastructure with almost 0 environmental impact in the broad sense, also transport, for instance. So this way, we want to be a step before the problem occurs. Our research topics are therefore climate resilience, energy reduction, and resource optimization, and using new technology and management, exploring mechanisms and designing new materials. One of these aspects is data, not just using it, but by means of knowledge, open source accessibility, it's important, I come back to that, insight and expertise, adding important impact on society and industry. So why not a continuous updated LCI, for instance? And indeed, if we want to solve future challenges, we need to go towards BIM, Building Information Modeling. In a publication, Shaping the Future of Construction, BIM is the most promising technology with highest impact. So many of our research topics are part of 2 goals. The development of a smart pavement performance model, including climate change, traffic, aging, healing, fatigue, based on historical and actual data. And on the other hand, the development of a smart selection model for assigning the use of REP. We have REP, so let's use it smart. So we work more effectively by detecting and defining these future problems and the parameters, and use historical and current data to build these models. These models will be fed by simulated data from macro level, the roads, traffic, even towards molecular level data from the microscope, for instance, or the rheology. Only that way we will understand the mechanisms and get solutions for the future proof. We don't need to design asphalt for today, we need to design asphalt and materials that can resist climate change in future within decades. Here you can see our main research topics to develop sustainable and climate resilient road structures by using intelligent systems and sensors for monitoring, data-driven analytic modeling from micro to meta scale, LCA, LCSCA assessment, development and implementation of sustainable technologies for end-of-life solutions. The second research line is material research and optimizing test methods in order to anticipate to the upcoming climate change implications. This research is done on nano. We come back to that later too, with the two presentations, and macro scale, and use innovative rheology and materials, such as biobinders, regenerators, titanium dioxide. Further, we want to reduce their environmental impact and footprint and use all these data into the development of this asphalt performance response model. Now, in order to support these both research lines, I already discussed these topics, we can count on 25 junior and senior members, and some of them are attending this meeting. And we have also a well-equipped asphalt laboratory with most general and some specific test devices. And also we are proud on this, an extensive bitumen lab consisting of physical, chemical, and rheology test devices and microscopes, giving a physical view on the material on a very small scale. Last but not least, maybe this is also the strength of our research group, we manage several test tracks in order to monitor our research on a larger scale, but even more important, on a longer term and under real conditions. So if you need more information, you can check our website and attend our yearly organized Asphalt Innovation Symposium every year in December in Antwerp. Here I listed some possibilities for future collaboration in education and research. We welcome partners to give a guest lecture, for instance, participating in trainings, invite even students to the E&E Congress and seminars. You can also collaborate in our research as a funder or a partner, supporting PhD students, bringing stakeholders together, and most important, providing data from the binders or materials for our models. And an open source, why not an open source reference sample, which we can use as a round robin just for research purposes. So I hope that I convinced you that we have ambitious strategies with excellent resources, so we are the ideal partner for you in future researches. I want to thank you. I also added a list of our current PhD projects, students, and other current projects ongoing with industry in this presentation. We send it later to you. But if we have time after the discussion, we can come back to these projects if you are very interested. So now I would like to give the screen and also the words to Georgios.
Wim, sorry for interrupting. Just a quick question. Would you like to accept some question and answer some questions now, or some comments on the introduction you just gave, or would you prefer to have that at the end?
Maybe at the end, so that we can come back. We have these presentations, unless there are very urgent questions. I don't know, are there already
No, we don't have any in the chat right now. Just wanted to make sure. So everybody, please take note of your question. Thank you very much.
Okay.
Welcome, Georgios.
Hello. Let me share my screen first. I hope that you can see my full screen. Welcome from my part. My name is Georgios Pipindakos, and I'm a PhD researcher and academic assistant at the University of Antwerp. I'm currently finalizing my PhD work under the supervision of Professor van den Berg and Dr. Sunen from NINAS. And I would like also to thank you for the opportunity to give you a taste of our research at the University of Antwerp. And the title of my presentation is actually Aging of Bitumen Behind the Scenes. And with this title, we would like to highlight actually what is seen with the aging of bitumen and what is behind this in terms of chemistry or microstructure, which is not, let's say, a phenomenological consequence of aging. For that presentation and to ensure that this will go smoothly, I have included in today's menu some background regarding aging, and then the presentation is split in three core parts, one about the experimental proof for the aging mechanism of bitumen, and then we will dive a little bit into microstructure of bitumen and the effect of aging on the bitumen surface microstructure. And the third core part, which actually is apparently of more interest, is the link, or let's say the statistical framework that we have proposed in order to link the fundamental changes in chemistry with rheology of bitumen. And finally, since this is a menu, I have included some food, in this case, some food for thought from this presentation. To begin with, unfortunately, for the different stakeholders of the bitumen industry, as time goes by, our material, since this is organic, suffers from a phenomenon that is widely known as aging of bitumen, and this has as a consequence different distress type in the final mixture of asphalt roads. One of them you can see actually in the right up part, which was nearby our campus, more or less when I arrived also in Belgium from my PhD research. This phenomenon of aging is quite complicated in terms of investigation, since it's a multi-phase and multi-physics phenomenon that we can study from different perspectives and scales, starting from on-site and going down to macro meso and also to binder scale, and this can be distinguished either to nanoscale or even to molecular scale. Of course, the phenomenological performance of bitumen, or in other words, the mechanical and rheological performance of bitumen, is also of importance in order to see in the upper levels how this behaves. Fortunately, at the University of Antwerp, we have a well-equipped lab that we can perform different physico-chemical analysis and also rheomechanical analysis in bitumen and asphalt. But my PhD research is focusing only on the binding medium, in this case, our good friend bitumen. And I'm focusing mainly on two scales, the microstructure and rheological performance and the chemistry of bitumen that we study via molecular investigations. Having this in mind, I will actually briefly mention the hypothesis that exists until nowadays for the molecular scale of bitumen with regard to aging. Previous scholars have reported that aging can be split in two rate determining phases in terms of chemical reactions, one fast and one slow rate phase. And they have proposed also different chemical paths. For example, one of the most popular ones is that already around 20 years ago that proposes that a model compound of bitumen, in this case a dihydroathracene, can react with oxygen, and after some intermediate products like hydroperoxide can either decompose to organic free radicals or can be aromatized and can be accompanied also with the formation of sulfosides. This refers to the fast rate reaction, and the role of free radicals was considered to play an important role for the continuation of the second phase, which is the slow rate determining phase. However, these are hypotheses that have been proved not to much extent, apart from sulfoside and carbonyl formation that has been observed with Fourier transfer infrared spectrometer. Why we are now considering to understand chemistry? Of course, it's obvious that chemistry is the more fundamental way to understand changes in rheology. For example, in the left you can see how rheology affects, for example, the master curves, rheological master curves, and there are obvious changes with aging, with standardized simulations like rolling thin film movement testing and pressurized aging vessel, that they increase the complex modulus and they decrease the phase angle. These are known changes because of aging in rheology, but also there are other effects of aging in extracted from master curves, rheological parameters, but also in different chemical variables, for example, changes in solubility or polarity-based fractions of bitumen, widely known as SARA fractions. I will not go in each one of them in detail, but what I would like to highlight with that is that chemistry is probably the key to understand changes in terms of phenomenological changes like rheological and mechanical ones. And my PhD, actually the objectives of my PhD involve, among others, an experimental validation for this aging mechanism about the chemistry, but also not only with isotherm conditions, but also what is the effect of standard simulations that we use in the lab, like RTFO and PAV, how these are affecting the chemical paths and the oxidation products. And I would also like to give you a taste of what link can we find until now between chemistry and the apparent bitumen surface microstructure. And finally, one of the goals of this PhD work is to provide a framework, statistical framework, in order to link the chemistry and rheological changes because of aging, and to model them finally, which is something that I will not go through in today's presentation, to model it via a continuum thermodynamics approach, or more specifically with thermodynamics of irreversible processes, which fit pretty well to an irreversible process like aging. I will jump now to the first core part of my presentation, which is the experimental proof of the aging mechanism that we have provided to some extent. For that reason, we have used three different binders that they vary considerably with each other, not only in terms of empirical performance or penetration and softening point, but also in terms of crude source, since they vary in crude source, and also in terms of distillation process. Binder C, more specifically from this table, is a product of fish breaking process, and also included waxes. So we tried actually to vary the binders as much as possible, so that we can conclude if the mechanisms are more or less universal or not. For that reason, we used a kind of modified aging simulation, having thin film oven testing, but in a different temperature at 50 degrees. And in order to accelerate from realistic conditions a little bit the process. And different time intervals from 0 to 2 months were used with different spectroscopic techniques, which I will go in detail in the next slides. with the goal, of course, to capture intermediate and final products of the hypothesis that existed until nowadays, and to review if this hypothesis and the aging mechanisms are valid or not. The key points that I will also present more clearly in the next support that indeed we have two rate determining phases. It was also the first time that we were able to capture for bitumen and oxidation of bitumen organic carbon-centered radicals with an advanced spectroscopic technique which is called electron paramagnetic resonance. And also for all the binders, we saw a clear transition between the two phases, the slow and the rate determining phases. And finally, the time of flight secondary ion mass spectrometry, or in short TOF-SIMS, was used in order to find more details about the oxygenated products after this transition point, which was found for all these three binders around 8 days. The first technique, which is the most common one for research purposes and is used widely, is the Fourier transfer infrared spectrometer, or FTIR. In the left, you can see spectra and how this evolved over time. And in the right, we have isolated the normalized sulfoside intensity, which is considered one of the products of the fast rate phase. And we can see from this oxidation kinetics in the right that all the binders fit in a model that takes into account the fast and the slow product, or the fitting curve is actually based on this model, and the parameters were extracted from this model. And this supports indeed that from FTIR we can separate the fast and the slow rate phase. However, as I mentioned in the beginning, it is believed that from the fast rate phase there is a different chemical path that also creates radicals, organic radicals. For that, we used, as I mentioned, an EPR, and from the spectra, as you can see, over time, we were able to isolate organic carbon-centered radicals, and secondly, different metal species, in this case, vanadium ions. This was performed via MATLAB, and we compared the simulations with standard libraries for spectra in order to find information about these radicals. After processing, we were able to plot in the left the number of spins of the organic carbon-centered radicals over time to have again oxidation kinetics of the organic radicals, and in the left of the vanadium ions. First, we tried to fit it again with a fast and slow rate model. However, one of the binders even give a negative coefficient, which is against actually such a model. Then a mono-exponential model of only a fast rate phase was used, and this fitted for all the binders. And the interpretation of this for the organic carbon-centered radicals is based on the fact that oxygen-centered radicals, which according to previous hypotheses for the chemical paths are produced, yield to carbon-centered radicals during the fast rate phase, and afterwards during the slow rate phase, the rate of production and formation most probably is equal, and for that reason we observe a plateau in all the binders, independent of the binder type, source or distillation. On the other hand, metal species like vanadium ions were almost unaffected by aging, considering the standard deviation of the replicates that were performed. And this based on different reports and publications for crude oils, not for bitumen, can be an indication of the vanadium content of bitumen in this case, and further research as well will investigate if we can trace back from this the source of bitumen. Having to some extent support that we have a clear transition from the fast to the slow rate phase around 8 days for these binders, then at this time interval at 8 days with this thin film woven testing, a TOF SIMS was used. The principle of this technique is based on the fact that we bombard the bitumen surface with bismuth ions, and the emitted ions, if specifically are energetically charged, they can give information for different oxygenated products. For example, about sulfoside-containing fragments that exist before and after aging in the bitumen surface, as well as hydroxyl-containing fragments. Also, other information for polycyclic aromatic hydrocarbons and other information were extracted. Here we will focus on oxygenated products, which all were increased after the completion of the fast rate phase, independent of the binder used. And this supports to some extent the FTR data, since all the sulfoside-containing fragments in the left and all the oxygen-containing fragments in the right were increasing upon aging, and especially after the completion of the fast rate phase. With TOF SIMS, one is also possible to extract from this bitumen surface that we bombard more information, like high-resolution images. High-resolution images, especially for one of the binders that was used for the Vaxi binder C, showed a clear difference before and after the fast rate phase. Here you can see the high-resolution images of this binder, which only showed some clear differences in terms of chemical mapping, and more specifically the aliphatics in the bitumen surface were less pronounced after the fast rate oxidation phase. This fact triggered us to investigate more Vaxi binders after aging, and more specifically to focus on the bitumen microstructure triggered by these chemical differences in the surface microstructure. So this shifts to the second core part of my presentation, where I would like to show you different observations before and after aging for the bitumen microstructure. Until now, it is widely known that for bitumen, and specifically for the surface microstructure of bitumen, there is a peculiar pattern which is called the B structures. Of course, the Bs are not look like the ones that they are visualized here, but the first presentation of these ripples with yellow and black color from Luber and his co-workers looked like bees if you see them in a top view or in a topographic microscopic image. And for that reason, bitumen research and terminology have adopted these B structures in bitumen. In the right, you can see actually a section of 1B, and the heights and valleys actually are the dark blue, dark yellow and dark black colors in the top view. You will see later a microscopic image how exactly it looks like. For the origin of these B structures, now there are two schools of theories. One supports that these Bs in the surface microstructure are because of the paraffinic waxes that bitumen could have. And the second one believes that the more polar actually fraction of bitumen, the asphaltenes, are the reason behind these B structures. In this study, we adopt the first theory of school, and for that reason, we used 4 different Vaxi binders, binders A and D, and 2 Vax-free binders. The presence of Vax was justified based on differential scanning calorimetry and the melting enthalpy, which was only observed, of course, in the Vaxi binders. It should be noted that binder C and F, which were Vax-free, they didn't show any features in the surface microstructure before or after aging. So the focus was only to the Vaxi binders, and for that reason we investigated Vaxi binders before and after standardized aging simulations of RTFO and PEV. In this slide, you can see for the bind array an example of what advanced microscopic techniques can capture before or after aging. In the left, you can see topographic and 3D height images of a confocal laser scanning microscopy that we possess in our labs. And in the right, images, topographic and phase contrast ones with anatomic force microscopy or AFM. Some obvious observations before and after standardized simulation in the lab is that the number of bees is decreasing, for example, and this is confirmed from both microscopies. And with AFM, with phase contrast, we can also observe a second phase of these bee structures, which is called the periphase, which is not really obvious with the confocal laser scanning microscopy. After that, let's say, human-based observations, more sophisticated editing images, editing software packages were used that accompany these two microscopies. And we were able to isolate the bees based on height thresholds that were imposed for the peaks and valleys. And we extracted for the vaccine binders before and after aging different metrics of identification of the bees, like the bee percentage and the number of bees which are normalized per square micrometer. The key points of this study support that there is a clear decrease of the bee percentage and the number of bees per area. And this is of importance since if one considers that these bees have an association with the waxes in bitumen, which most of the times create deposition problems in the different stages of processing, we can understand more about their crystallization with aging afterwards or with oxidation during the different stages, also from production until paving of bitumen. Also, the two techniques, CLSM and AFM, the two microscopy techniques, are in good agreement, as you can see in the bottom left, with regard to the bee identification as expressed, as witnessed by the bee area percentage. Also, other values like C probabilistic values like kurtosis and waveform characteristics like the wavelength of the bees have been extracted. However, the effect of aging on them was not clear. In the third core part of my presentation, since I would like just to give you a taste on all of them, if you are interested, always you can find information with regard to the corresponding publications in the bottom of the slides. This is our latest study that takes to account a statistical framework in order to link chemistry and rheology. For that reason, the same three binders that I presented in the first study for the experimental proof of the aging mechanisms were used, that they were varying considerably in terms of distillation, source and type. Were used in 4 different aging states, standardized ones, RTFO and PAV was used, and also the original binder unaged. And also from the first study, the time interval at 8 days was used for all the binders with this modified thin film oven testing, since it was considered as the completion of the fast rate phase and the initiation of the slow rate phase. Then different methods were used, spectroscopic techniques that showed great potential, but also protonuclear magnetic resonance, which can give us an information about the proton regions. And also rheological testing, typical frequency sweeps with dynamic shear rheometer and viscosity tests that were performed with Cap and Bob. And after constructing master curves, different rheological parameters, indicators, which are not standardized ones, but they have a meaningful, they are more meaningful in terms of distress types according to literature, were used. I will go through them in short in a next slide. And all these were then implemented in a statistical framework by using more advanced statistical techniques like bivariate analysis, non-parametric tests, hypothesis tests like the Wilcoxon exact rank sum test, and also multivariate data analysis like factor analysis, and at the end step of it, which is similar to multiple linear regression, which is called factor analysis regression in this case. The objectives of this study was first to compare what is the effect of aging in chemistry and rheology if we use different aging protocols, standardized and non-standardized ones. Secondly, if we are able to link somehow via statistical framework the changes in chemistry and rheology, taking into account aging. Changes in rheology are obvious. As you can see, for the two binders, there is an increase of complex modulus and a decrease of phase angle, and probably it's not completely obvious, but there is an overlap with RTFO, so the short-term aging as simulated in the lab, with the completion of the fast rate phase from the aging mechanisms. But of course, this is just a visual observation, and for that reason, statistical analysis was performed in the master curves, and more specifically in the parameters of them. The key points of this study is that we propose a training data set of 3 binders that they vary a lot between them in order to link effects of aging in chemistry and rheology, and also to show that there is a great potential for statistics and multivariate statistics for bitumen applications, especially if the library of this dataset can be expanded in extracted binders and also modified ones, since this study, this PhD work focused only on conventional binders. With regard to the rheological parameters that were extracted from the master curves, I will just show in brief here in this table. One can extract different crossover values which they have indication, for example, for cracking. Also the shape parameter R, which is actually the logarithmic difference between the glacis modulus and the crossover modulus, can give us some indication about fatigue cracking. All these values, of course, have a clear evolution with aging according to literature. And finally, some of the most prominent values that are used nowadays in for scientific purposes are the Glover rho and the delta TC value, that they are related with non-load related cracking and aging-induced cracking. The formulas and the relations of them are given. In case that you are interested to know more about them, of course, I would be glad to discuss them after my presentation. All these values are extracted after you construct master curves, and so you need a variety of different temperatures in frequency sweeps in order to construct the master curves, and also low temperature should be taken into account in order to extract the delta TC value from different geometry of parallel plates in DSR of 4, 8, and 25 millimeters. Then all these parameters, the rheological and chemical parameters, were implemented in statistical softwares, and we first compare the short-term aging and the completion of the fast rate phase from the aging chemical paths. And for that, we perform first the bivariate analysis. Here you can see the bivariate analysis for the chemical and rheological parameters. And this allows us to judge if the correlations between two data sets, this expressed from the Pearson's R, is strong enough. And this, of course, is supported by the p-value of the Pearson's R, which shows actually, in other words, the probability that this difference is random or not. And both show that the values that are captured are they have a good correlation between the chemical parameters of the two different aging states, and also the chemical and neurological parameters of them showed a good correlation between the states. Then each parameter was also scrutinized in terms of differences for the medians, and this was done with Wilcoxon exact sangram test, which is a non-parametric hypothesis, statistical hypothesis that shows actually what we were searching for, if the differences for one parameter only are considerable. Also, the Wilcoxon test supported that between the two states we have a good agreement for both the rheological and chemical parameter, which in other words means that rheology and chemistry, independent of the aging protocol that is used, if one coincides, for example, rheology, then chemistry at some extent follows the same trends. The next step was to perform multivariate data analysis, and for that reason the chemical parameters were imported in a technique that is known as factor analysis. It's a kind of re-expressing your data in a number of smaller factors, and the number of factors actually that you will choose are based on the fact that they should express at least, as a rule of thumb, the percentage of total variance at least on 70%. For our case, all the chemical variables were expressed adequately with 3 factors, and also a pre-requirement I should mention is that one should perform correlation matrices, so that there are some correlations to do a factor analysis. And here in this graph, you can see actually the factor loading plots, which show, similarly to Pearson's R, each chemical parameter, what is the correlation of each chemical parameter with each of the factors. Also, the ray, the length of the ray shows actually how extensive is this correlation, and the close the parameter is to the y or x-axis of, for example, of this circle, shows if it loads heavily to factor 3 or factor 1, for example. For example, from this graph, one can see that sulfoside-containing fragments loads heavily on factor 3, whereas all these chemical parameters load heavily in factor 1, and it was shown afterwards in more details that all these parameters actually are able to distinguish the fast and slow rate phase. However, the factor analysis is not the end step, but this is a kind of intermediate step before one goes to a kind of multiple linear regression, which, as I mentioned, is called factor regression analysis. And this is used in order to predict some variables, so to construct some models. So one can extract first the factor scores from the factor analysis and to predict a specific rheological value. Here in these two graphs, you can see, for example, what is the predicted value from the statistical framework for one of the rheological parameters that I mentioned previously, the delta TC, and what was the actual one that was measured from DSR testing. Also, for both, the correlations was the best that were observed. Also for the same parameter R, which shows the width of relaxation of your master curve. But for more basic parameters, rheological parameters like viscosity, it was shown that, which is not presented here, it was shown that if one overloads actually the model, then the prediction probably is not the best. So for less basic parameters in terms of rheology, and not more advanced, that they are based on different calculations like the delta TC, one should not, let's say, overwhelm his model. The degree, of course, of fit between the actual and the predicted values can be expressed from the coefficient of determination, and the closer is to 1, the best is the correlation that one can succeed. This brings me to the last part of my presentation, the food for thought. And I would like to highlight here that spectroscopic analysis have great potential in terms of understanding the chemistry of bitumen, and also microscopy can accompany these changes in chemistry sometimes. And also, since until nowadays there was not a clear increase or decrease of these B structures in bitumen, we tried to tackle in this PhD project some obstacles that existed until nowadays. We also have proposed a statistical linking framework using a limited, of course, amount of binders that nevertheless they vary considerably in distillation, crude source and performance, and this can consist a training data set. In the future, we are targeting to expand this library, including more vaccine binders, also extracted from site that we have the information, of course, for the binder itself, and also modified binders, and this will be used as validation data set of our statistical analysis. Of course, in case that you are interested in this study or you see some potential from your side, we would be glad to collaborate with you in different aspects. To name some of them, as I mentioned them as open calls, there are different projects that we are running. The first one is about the quantification of real-time kinetics of bitumen's microstructure. For this, 5 different research groups from 4 universities, we cooperate, and there is national funding for that. And we are now in search of more vaccine binders so that we can investigate the cooling and heating effect of the real-time kinetics on these B structures, and to link them also with other information, for example, with information about the crystals, so crystallography and differential scanning calorimetry of the vaccines. So in case that you would like to cooperate with us and you possess such vaccine binders, we'll be glad to discuss it further. For that, I have included a QR code that we can discuss certain aspects. You can scan it, and it will direct you, of course, to some contact information of mine and my PhD research. Secondly, since I'm finalizing my PhD work, and I will also would like to continue at least in academia, I'm thinking to continue this work in not only to conventional binders, but also to extract it from on site, and also the information of the time that we're on site, as well as the original binder, are of importance for that. So in case that you think that you would like to collaborate with me and our group on this aspect, we'd be glad to discuss further details for example, for a postdoctoral proposal that we are considering. For last, I have kept 2 global groups that our university leads. The first one is called Young Aging Crew. Is a group of 40 PhD students around the world that I and the University of Vienna and Aston in UK, we are leading. We are 4 PhD students that we are leading this group, and we are considering different aspects of aging from macro to nanoscale, for example. And the main, let's say, the common spot is actually aging. So in case that you have a data set that you would like to share with us, we'll be glad to work more on these data sets, for example, with statistical analysis. Finally, there is a group of 17 universities around the world from 4 continents almost that we are tackling now the opposite, let's say, effect of aging, and for that we are trying to find potential antioxidants to prohibit aging. and this will be independent of the binder source. So every group and every university will work with his local binders. In case that you also possess such a binder that you are interested to know more and is a conventional one, also you can contact us on this direction. I would like to thank you for your attention. Of course, the contact information are always provided to you, and we would be glad to discuss now or later specific aspects if there are also questions from this presentation. Thank you very much.
Thank you, Georgios. Oh, now I hear myself. I understand that also you would prefer to have the questions and answers after the next presentation when we can have a joint session?
Yeah, I think it's preferable for everyone, I guess, so that we have more time for questions.
Fine.
Yeah.
Fine. Thank you very much, Georgios. Then it's now over to Johan.
Okay, thank you. I will try to share my presentation. Can you see my presentation?
Perfect. Thank you.
Okay, I will put it on the full screen. Okay, thank you for the opportunity to have this talk. And my presentation is a continuous of the work of, yeah, it's a little bit the same, but I'm for a longer time in the investigation of B structures. So I'm going to present some work of the last years. It resulted in some papers and some interesting work, also the work of Georgios. And the title is New Insights of B Structures. One is, of course, the inventory. So we'll give a short introduction, some objectives. I will show you the materials and the setups we are working with, the methodologies and the pros and contras of some techniques and methodologies, some results, and then the conclusions. So I will start with this image, and I found this a very fascinating image, and it's an image of a paint surface. And one of the effects when paint is drying is that you can have this kind of wrinkling effect. And yeah, this was a little bit an inspiration of, we have the same wrinkling effects in the surface of bitumen called the B structures. And when you look into literature, there is still a lot of uncertainty about that. People are still not really all on the same wavelength in order how these structures are formed and what they are representing. And that's something we wanted to show. The idea was, or objective or research question was, can we generate B structures? Can we make them ourselves? So, and the idea was, if we take straight saturated hydrocarbons of a certain length, so waxes, if we put them in bitumen, can we then get some B structures at the surface of the bitumen? So we set up a plan, and we worked with two setups. We used the atomic force measurements equipment, which we could use from the Vrije Universiteit Brussels. And then we used our confocal laser scanning microscope as an additional tool. So we had two techniques, and we started with paraffinic bitumen because we knew there were some bees in the surface there. We could observe them. And we also knew that if we have wax-free bitumen, that we don't see any bee structures in the surface. By adding these waxes, we could generate these wrinkling effects, and this occurs in these bees, and we could observe them both in AFM and in confocal microscopy. We also wanted to see if it was possible to make bees in oil or in maltines or in covered surfaces. So what we did was half of the surface was covered with with a glass, and then the other half was open to the air, so it was a free surface. And we could clearly see that the effect of covering influences the generation or the propagation of these bees. And what's also something we saw when we did some experiments in the bulk. We never saw bees in the bulk because there it was not a free surface. So the setup in Brussels is the AFM. It's a very sensitive machine, so it's placed in a special cabinet, so there are no vibrations, or that's the aim, to get a minimalization of the vibrations. And you can see on the left-hand side the nanotube or the cantilever, and it's we call it a non-contact method, but it's very difficult to provide or to have no contacts because in the beginning you don't know what the heights of the bee will be, and so you have to set your accuracy. You want to have very accurate images. It means that you want to go over the surface as close as possible, and if you have large bees, which you didn't suspect it, then you can have a collision with your sample. So it could be very tricky, and also bitumen can be very soft, and then of course the needle can be contaminated, leading to disastrous measurements. Our confocal microscope, the microscope contains two techniques. So there is an optical confocal microscope in it, and there is a laser. So we can use in this machine both techniques. So we can have an optimal, confocal optical image. We can go up to almost 24,000 times magnification. And we can make a 3D scan with a laser of the specimen. So that's a very advanced machine. And there is this is really contactless. So you don't have contact with the sample. So you can work on hard and soft and even liquids. That's all possible. So if we look to some images, on the left-hand side, you see AFM. I show two images from the AFM, the height and the face. So George has also already showed some images. These are, I think, the same sets of images. And you see that indeed, if you have virgin paraffinic binder, that you can see very similar images of AFM and confocal laser scanning microscope. So the topography of the surface is the same and the images are the same. And then if you age them, you can see a difference in the amount of bees and also the size of bees. You can also see in the AFM that there is a generation of another phase. But that's something George already told. And then at the bottom, you see clearly a virgin bitumen. So when there is no naphtemic wax in it, then you see that there are no bees or no structures in the surface. So the next step was we started to use these wax-free bitumen, and we added some different chain lengths to it, or canes with different chain lengths. So we started with 2 weight percent of C24, and then we saw that we couldn't see any bees. So we can see some phases. It seems to be that the wax is not really dissolving, and we have these different areas. And we could see this in AFM, and we could also see this in the confocal. I split the image of the confocal. On the left is the optical image. On the right, you have the laser scan image. So you see in the optical image the decolorization. So, and then on the other side, you see the laser scan. If we increase the length of the waxes, so the chain length, and we go to a C40, then at that moment we can see that we start to generate these bees, and we can see this in the AFM and in the confocal images. Also, if we take a commercial wax, like Cecil bead, If we add 2%, then you can see clearly again the creation of these bees. So we started then not only with one wax component, but we started to see if we combine short and long waxes together, and then we finally found some mixtures or wax mixtures which delivered us some nice bee populations. So you can here see that we started with adding short and 24s and C40s together in different weight ratios, and then we could obtain these nice bee structures. So it's clearly that if we add wax to a virgin bitumen, that we can generate these bee structures, and that is dependent on the amount of wax and on the combination of different C chain lengths. We also did it with a combination of a C24 and a sessile bead, and then you see that the bees becomes more like little drops, so we can see changes in the morphology of the bees. Here you see some drawbacks of the AFM. So what I told you, I made an image of a needle which was contaminated, and you can also see in the sample after that, that's an image I afterwards made with the confocal laser, that you have these scratches. So with a very soft bitumen, or if you could not really adjust the height in a proper way, you could have contaminations with them. And of course, it's impossible with an AFM to measure on fluids. That was our true glass. You can only scan a surface, but with a laser confocal microscope, you can measure through glass. So you have the possibility to measure through a transparent medium. So you can measure through oil, water, or glass. And what you can see here, if you cover it, the one side is covered with glass. So you don't have a free surface. When you don't have a free surface, there is no, there will be no bee structures. So you clearly need a free surface in order to generate this wrinkling effect. If we put it underwater and we measure it, we can see the same. You see no origin of bees. So again, a clear surface is essential in the propagation or the development of the bees. Then what we did is we took just an oil and then we put some waxes in it. And what we saw is that we even could generate bee structures. So you see the A, that's are the images on the top of the oil surface. So you can see that you can generate these bee structures at the surface. Of course, it was very difficult because these you need to stabilize it. It's a liquid, so and during scanning, vibrations are really influencing your measurements, and that was a very tricky one. So you can see some horizontal lines due to vibration. In the middle at B, you can see still some wax crystals. So that these are pieces of wax which are moving up to the surface, where they then start to form these bee structures. And at the bottom, we also added some filler in order to see what will happen at the filler side, but we couldn't see any effects there. Then we also took some maltines. If we look at maltines, we can see no bees, but if we add some a wax cocktail to them, we can also generate these microstructures. So we see the crystallization and we see the bee structures occurring at the surface. Then we had some shortcomings, of course, with the confocal laser microscope. One of the shortcomings is that, of course, an AFM is more sensitive. and that played us a little bit. That played a role in the measuring of these secondary phases. So, but if we combine optical and laser, we still could see the effect. So the lowest scale or the resolution of the laser is around 5 nanometer, and if you look at the profiles from or the height differences, you can see that of course phenomena lower than 5 nanometer we cannot observe. So to finalize, yeah, we can see that these methods give more or less the same results. They are we can use them both. AFM is a little bit more sensitive, but has drawbacks that it can lead to contact and contamination. The confocal laser microscope is very handy and very fast. And then, of course, we can work on very soft, even liquids. We can look through surfaces. Yeah, one of the things we are thinking about, or where we are working on, are now emulsions, for instance. So we can also continuous look at changes in the microstructure. You see that unmodified or bitumen without wax is not showing any microstructure. For us, it's very clear that these microstructures, these B structures, are formed by a combination of different N-alkanes. So different chain lengths will result in these B structures, and we can correlate certain chain lengths and certain combinations to certain morphologies and certain distributions of bees. And then we also see that we can also generate bees in oil or in paraffinic. So there is no interference of asphaltenes or other bitumen components needed. So it's clearly due to the crystallization of the paraffins. We already published some things in. There was a very nice publication in View, and we also did some other publications. And here you see a photo of the things we are working on now. Also, George said something about that. So we build us a Peltier heater, so we can cool and heat up bitumens, and at the same time we can look with our confocal laser microscope to the changes of the microstructures. So that's one of the things we wanted to do in our scientific research network. I'm the promoter of that research network, so we are still looking for collaboration with the sector. And of course, one of the other things I'm looking for or working with is I'm also leading the group of RILEM on the fume emissions, and that's also something I want to work on in the future. So thank you for your time, and if there are any questions, I'm glad to answer them.
Thank you very much, Johan.
Yes.
Thank you very much. Thank you very much, Wim, Georgios, and Johan, for these insightful presentations. Congratulations to all people involved in making this research possible. And now I think it's time for the questions and debate. I don't know if there's any question in the chat or someone who wants to jump in and ask something to our friends from Antwerp.
There is no question currently in the chat. Somebody raised their hand. Yes. I just wanted to mention this, how we want to run the questions and answers. If you please raise your hand. If there are more hands raised, then we can also see the order. So we do have a question, and I will in a moment share my screen again. Maria, Gonzalez has got a question. Remember to unmute yourself.
Hello, good morning. It is Maria Gonzalez from CEPSA in Spain. So first, I would like to thank you for the very nice presentations. And I have a question I would like to ask to Georgios, and it is related to the assessment of aging in PMBs. Right, from your point of view, and considering that maybe in the future you will work on this kind of materials, which would be the most useful tool for studying the chemistry behind the aging of PMBs? In this case, we have the polymer as well as the bitumen. So I guess that maybe, I don't know if IR spectroscopy or other of the techniques that you have used would be useful for this material.
Yeah, thank you for your remark. Actually, yeah, indeed, in the future, we are considering to shift to polymer modified binders, since at least you should start from somewhere, and to start from conventional binders was the first point. We tried to vary in the beginning different aspects of conventional binders. Of course, modified binders, they have more difficult in terms of unraveling the mechanisms and the aging mechanisms, but and there actually the polymer degradation is something that we should compensate in terms of aging or not. We have done some limited research on rheology and FTR spectroscopy for now. There are some potentials and some tools to, let's say, identify what is exactly aging for the binder and what is the polymer degradation. But of course, in case that you would like to discuss this further, and you possess also some materials that let's say we have some information about the polymer content, for example, since these play a significant role for the aging degradation and polymer degradation in general. That would be really a nice opportunity to discuss further if we can see a potential out of this future study. So yes, Maria, we can discuss it, I guess, in more details via email. But we are for sure directing now, since at some extent we have shown experimental proof for conventional binders, to go in the next step, which is modified binders. At least we should start with polymer modified binders.
Okay, thank you.
Yeah.
Thank you, Maria. And Georgia, Maria, please remember to lower your hand. Otherwise, I will always think that it's a new hand, but it might well be. Thank you very much. Maybe are there any similar any questions related to the question that Maria just raised, or the answer Georgios have given? If not, I would like to suggest that we start in the order of presentation. So maybe with Wim and the introduction Wim has given, as well as the overview on research activities at the University of Antwerp. Just as side information for participants, it might well be that I mute yourself again if there are too many background noises, so don't forget to unmute yourself. So, any questions to Wim? Or I take the opportunity that I'm now unmuted to ask a question. When you, on slides, I think 10, 11, 12, something like that, when you were talking about BIM, you also mentioned reclaimed asphalt pavement RAP, which I think is, it's not only an asset for the for asphalt pavements, but also with regard to, for example, sustainability, resources, that is virgin materials, etc. So there's an asset for the asphalt pavements. But then on the other hand, I think there's also an issue about who knows what's in there and what about when we are thinking in sustainability planning? Then if you take the end of life of a construction works, for example, into account, or want to take that into account in your, for example, life cycle assessments, etc. Can BIM help? And if yes, how can BIM help to manage, for example, reclamation of asphalt, the quality, the quantity, the details about that, so that they can be taken into account in planning activities? It's a question mark. I've got a big question mark behind that, but maybe you can help.
Yes, thank you, Anja, for this question. Yes, it's a big question mark for all of us. But now, in Flanders, for example, we are starting with this BIM for infrastructure works. That means that they are, making material passports a little bit on the one side, but also adding information in this BIM environment. That means that if they are now designing a road or reconstructing a road, that they add properties such as layer thickness and mixture type, only the type of mixtures in this BIM environment. Now, what we want to do is in future, within a couple of years or decades maybe, because we need sufficient data to relate the composition of asphalt, that means the aggregates, but also the binder. Probably the binder is the most important factor. We want to relate that with the service life. As you know, that my colleague Ben Moans, a PhD student, is also diving into the LCA, LCCA aspects of asphalt and whole structures. And we need this service life to take into account in this LCA study. However, we don't have sufficient data. So there are many aspects related to your industry which could be supporting this model which we are designing now, to select on beforehand and estimate on beforehand the service life of the different layers. So on beforehand to estimate when when a certain layer in the structure is end of life. If we know that on beforehand, then we can assign this layer, the volume of material, to another work. And we can then use also other parameters like transport, the use of a certain type of rejuvenator. Maybe the type of rejuvenator will depend on the type of bitumen, the aging state, but maybe also the composition of the bitumen, modified or not modified, or even maybe with fibers. So if we have this data on beforehand, then we can feed our model with this data, and via the machine learning, it's a hot word, hot topic, machine learning, we can start working on estimating and predicting service life of roads, and optimize it on a macro level. So, for instance, that our Flemish Road Agency, but also the other agencies, that they can plan their job or all their works in a certain area or a certain period to each other, that we can reduce the impact, and not only the carbon footprint, but also the whole environmental impact via LCA based on this data. But then we need this data. Another aspect is that if we have sufficient data about the binder type, we are doing a lot of tests in the lab, only on the binder, sometimes also on the asphalt, but on the binder. If we can relate this performance of the binder in the lab to the real world on site, then it can also put into account in our model for this prediction and supporting the decision for the road agencies to select the appropriate destination of this typical asphalt, and not only based on the aggregates or on the mixture type, but also on the binder type. However, we don't have this data yet, so it can be a good discussion which data can be made available and can also be used in this data set. So yeah, I think that's the importance of BIM. Also, it's the next level. It's the next level for recycling. Also, maybe to add something, then we don't have to take course and recover the binder, because as we know that the extraction and recovery process of a binder can change the binder properties. So if we can skip that phase and predict it from our lab and our lab aging test, maybe that's also a good thing. To predict the real service life of not only asphalt but also for the binder.
Can I? Vicente raised his hand, but Vicente, before you were you were asking your question. Can I just ask a side question to that, or an additional one to that? I think it seems there are quite some opportunities in there, but again, for me to fully understand with this prediction, and I think I understand about the potential when it comes to the material as such, but how would in such a prediction, for example, the actual weather conditions, climate conditions during the lifetime, or the, for example, traffic conditions be taken into account?
Yes, of course. We have now, for instance, in Flanders, we started a task force to have a survey where all the data is available in Flanders. For instance, we have now a number of tracks, roads, where this climate data is also recorded and stored. Also the traffic. So these data we have, but we don't. And now we want to estimate or predict. I have to say. We need to predict the effect of the climate change on this pavement, but we don't have any data about what's inside that road. So if we have that, then it could be beneficial for this model. So we have this climate data already, and also the traffic data.
Okay, thank you. Are there any additional questions to Wim, his presentation, the work of the group at the University of Antwerp, their projects? Before we go into detail to the presentations and the work from Georgios and Johan.
Yeah, well, maybe you can give us a little bit, just a tiny insight of the list of projects you already mentioned.
Yeah. Okay, I will share my screen again. Okay. Okay. These are our current PhD projects. So we are, as you can see, they are a very broad spectrum of research topics. The aging, Georgios has explained his research, the aging of bitumen, the use of crump rubber as a modification in asphalt, the use of a heat exchanging asphalt layer to cool and to heat up the asphalt. Also related to increase of service life. If you have a reduction of the temperature interval, you can increase the service life of asphalt, and also increase the safety of the road. Then one PhD student is dealing with the texture of the road surface and related to the surface life, and also the degradation. Not really in the asphalt industry is one PhD student working with the geopolymers. However, she's combining RAP together with geopolymers as a road base material. Why? It's also part of our model. Our Smaragd model is that sometimes, or not sometimes, in some cases, it is maybe better to use RAP, not again in asphalt, and maybe now I expect some questions on or some reaction. But sometimes if you use the LCA LCCA method, sometimes it can be better to use RAP not in asphalt but in other materials, because it's just the environmental impact is just less than when you are, for instance, transporting this asphalt, this RAP towards an asphalt plant, which costs a lot of energy, of course. So she's dealing with that. And then Ben Moens, he's working on the LCA and LCCA. Maybe you know him. He's also involved in some task forces. And then a new PhD student is working on prospecting and mining resources in pavements. So he's trying to get sufficient data about all asphalt pavements in Flanders, and combining this with climate data and traffic data, and see he's working on this Smaragd model. And then one student is working on the application of titanium dioxide in photocatalytic asphalt pavements, also cleaning air and increasing the surface life. These are currently the PhD students. Currently, the PhD projects ongoing. And then for our projects with industry, I also mentioned here the Rejuvabit project. Some of you were involved in this. So we were using rejuvenators in 5-6 test tracks in Flanders, in base material, in base layers, in surface layers, and also using it in combination with polymer modified bitumen. Then I also mentioned this, the Road IT SciPads. It's already finished, but it is still worth mentioning it here, because this type of research output we are using in our models. So in this project, we try to define guidelines and also set the appropriate technologies to get sufficient data for this for the model. For instance, we use the thermographic camera for quality assessment, and we also use the smart compaction rollers, and so on and so on. And it's also used now in the port of Antwerp. It is part of the contract using this thermographical camera. Then in the port of Antwerp, it's a long-term project. It's again extended for 4 years. We are doing research and developing sustainable and innovative asphalt pavements for heavy loaded roads. And there we are using fiber Bragg gratings, which are sensors who could measure the deformation inside not only the asphalt, but inside the structure, so that we can detect damage before we can see it on the surface of the road. And in this project, we have several test tracks using these fiber Bragg gratings, but also using different types of binders, different types of asphalt mixtures and base materials, just to find out which structure, it's a standard structure, which structure is the best for this port area, and how we can optimize it in future. Because now we have some references, we have a reference mixture, we have reference binders, and we can optimize it when it is necessary. In the Recomat project, it's also finished, but it's also used in future research projects. We were developing this multi-criteria decision management model, but it's just limited now to asphalt and concrete materials. So the material flows in the port are there described. In the Aquabit project, we...
Excuse me, Wim?
Yeah.
Can I just ask a question to the slide before? Because it stated multi-criteria. Can you give examples of some criteria?
Well, yeah, it's for instance the rep, and also the transport distance. So it is the combination of different parameters, so that the port can decide which material will be used in another construction site in the port. So it is now based on transport and the rep material. For instance, if they have, okay. It's also part of this. It's a preliminary study, so we wanted to select these criteria, which is not very obvious. Then in the Aquabit project, we purchased this laser scanning confocal microscopy. Both of the presenters use this in their research, and we explore mechanisms like aging, healing also, to understand these mechanisms, so we can use this for optimizing these materials in future mixtures. Then the Crumbit Crumpave project is a project where we use the crumb rubber in bitumen and asphalt mixture. It is new for Belgium to use this material, so we are exploring this and optimizing it. In the Papua project, it's also together with the Port of Antwerp, POA is Port of Antwerp. We use these photocatalytic asphalt pavements, and now also one PhD student is assigned to this project. A new project, no, not new, it's halfway, is the foam, where we use the bitumen foaming technology in bound base. So we want to, also in this project, we want to use REP when it is not possible to use it on an optimal way in asphalt. We want to use it in situ by these in situ recyclers, and we are using there the foam. One of the researchers is now working on the bonding mechanism in this BSM, bitumen stabilized materials, on the foam part, not on the emulsion part. And then the Pioneers, that's a new project. It's really a large project together with 3 ports in Europe, where we have different sub-projects in order to increase the sustainability. But it's not only on the pavement, it is also in other aspects. But we are in charge of the pavement and also the green public procurement part to increase the sustainability of these European ports. And this one, it's upcoming. It started this year. We are monitoring all of our former test tracks now in collaboration with Road Agency and the Belgian Road Research Center and several contractors, so that we can learn from the materials we used 10, 15 years ago, but also our newest one from the Rejuvenate project, so that we can, if we drill cores, for instance, and we analyze then the bitumen, then we can combine it or relate it with our laboratory aged material, and see if we find some correlation. So this is also together with the Port of Antwerp and the City of Antwerp and the City of Beveren, where we used the EUB30 Power 3. It's aged bitumen bound base material, where we used old waterproofing waste material in combination with REP and 1% of bitumen. And that is, these test tracks still exist, so it's a very good material. Okay, so these are our some of our projects now ongoing or still. Yeah.
Thank you very much. maybe we have some more time for questions to Georgios and Johan. Do you have any more questions for them?
So shall we start with questions to Georgios then?
Mm-hmm. Maybe you have one.
Don't be shy.
Don't be shy. Yes. Do you think our laboratory methods for aging really represents more or less the future performance of the binders, or do you think we need to start considering other alternative methods than the one you already mentioned in your presentation?
Yeah, that's really a nice question, and there is a lot of discussion, at least in the scientific community, for that. To my perspective, I see different reasons that they are either pro or con for the standard aging emulations, for example, RTFO and PAV. But I also see that comparison with real conditions miss some points, and especially if one goes to the chemistry of bitumen. For sure, there are different chemical alterations that they take place in reality. For example, we have tested some extracted binders, and they show a different chemical pattern based on either severe aged with PAV and non-standard one, for example, 40 or 60 hours PAV, and they show some differences in terms of chemical products. However, I think that I'm also a supporter that chemistry plays a role in the rheology of bitumen. So having said that, I believe that we should consider also the chemistry and not only rheology, because the current standard simulations, most probably, they were initially developed in order to simulate in a good extent what happens in field. But in reality, probably only the phenomenological performance of them, and this is by means of, for example, basic properties like penetration or softening point, they are reached indeed. But if one considers more in detail the chemistry, we will understand that there is a big difference or a big gap between field-aged and lab-aged samples, or bitumen in this case. And the whole story becomes more complicated if, as mentioned from Maria previously, we go in modified binders, because there you have different processes that take place, also the polymer degradation that one should consider, and all of them, they counterbalance each other, and the whole phenomenon of aging is more complicated to be understood. However, to conclude on that, if we consider that we are only trying to approach the performance and rheological or mechanical performance with basic indices, then I think they are working sufficiently for our purposes. But if we want to have more detailed rheological properties, like, for example, ones that they can extract it from master curves, since they have a direct link with chemistry, at least this is what we have shown with this training data set of 3 binders, then we should consider to simulate more accurately what happens in the field. For example, there are different research groups in Europe that now they are working towards different patents of aging, that they also take into account reactive species in the atmosphere in order to simulate as much as possible what happens in reality. Also, another point of discussion, and with that I would like to close my argumentation on this, is that the severity of especially of long-term aging, if we consider it above 100 degrees, for example 110, this, based on what type of mixed asphalt one will use, could have considerably different chemical paths, because it has been shown for binder that over 100 degrees there are processes that in lower temperatures, they will never take place. And with that severe aging, with that severe temperature, and also keeping the standard pressure for PAV, this could have severe effect also on what exactly we are doing in our binder. We are just making it more brittle, but with other chemical paths, which normally in field they will never happen. That's what I would like to add maybe on this.
Thank you very much.
Yeah. Maybe, I don't know if someone would like also to share his or her ideas on that.
Actually, I think there's quite some interest in that, but sometimes also one needs a moment to think about that and reflect about that. But I think it's definitely something that we can specifically address, for example, in our next technical committee meeting or in task force specifications, when it's about discussing on how we might want to specify bituminous binders for the individual purpose in future. Question mark, I don't know.
Yeah, of course, I think personally that is a matter of debate that we can putting forward, but maybe if not now, but in some years, we reconsider our aging simulations. I think the first point should be that we should consider to reach at least equal chemical changes and then go for the performance. Since if we change considerably our binder, then we are just having at least phenomenologically the same performance in terms of penetration or softening point. But in terms of composition, we have changed considerably the material. So I think that's a point. Yeah.
Now, from a very practical perspective, just some practical experiences, and some of the attendees here will know perfectly well what this is about now. We are currently reviewing now on a standardization level the method of RTFOT in Europe, EN 12607 Part 1. And when we started with that revision, we also found out that we all had different interpretation about what does RTFOT stand for. And if you then start to dig into details, where was it developed for or when? And then you also think about, and which types of binders are we using now? And on the other, so it had been developed for a specific situation, that is production of the asphalt. Some now think it also represents the laying of the asphalt, while then it was developed for paving grade bitumen of a certain type. What about the conditions of production for asphalt mixtures, or what about modified bitumen? So I do think there's quite some need to discuss about that. But we have another hand raised, and that's Martin Fontenhoff.
Yeah, thank you, Anja. Exactly on that question about the RTFOT, we have tried to look at the aging of standard 7100 bitumen. Usually this is done by first short term, then long term, so RTFOT plus PAV. Now, and we saw a large aging in terms of change in rheology after the RTFOT step. So the PAV being much more strong than the RTFOT. And then just out of curiosity, we took the fresh bitumen and just put it into the PAV, pressure aging vessel, and did just the PAV. And surprisingly, the results were almost the same as when we did the RTFOT before. Would you have an explanation for that? So in other words, there's no need to do the RTFOT to assess the aging of bitumen, the long term.
Yeah, that's an interesting actually observation. Maybe if you would like to share my thoughts on that, I believe that as I showed also in my presentation, I believe that there is a link not only with production but also with the let's say evolution of some chemical reactions that they take place. So if one only uses PAV and reaches the same levels, for example, for a specific frequency in a master curve for the complex modulus, and the same with RTFO, that most probably would mean, as you mentioned, that there is no sense to perform RTFO. However, we should consider that before we pave actually our material, we should know in what state it is. So the purpose of doing the RTFO, I guess, was initially to show in what state we are paving bitumen. But of course, for the specific situation that you mentioned, I cannot comment more. There could be different reasons, I guess, that this could happen, but I cannot, let's say, imagine what exactly could be the reason that you reached the same exactly rheological levels.
Yeah, just try it.
Yeah.
Okay, thanks.
Thank you for that. And I noted that that's something that might be worth to discuss more in detail later. We have another hand from Mike, and I would like to remind everybody, I also need to look at the time. So I don't want to cut this short, but we only have 4 minutes left. And I would also like to invite for questions to Johan. So sorry about this. It's maybe too interesting. But Mike, you've got your hand raised.
Yeah, in fact, I had a question for Johan. So I don't know if you want to take that one now. I would love to have another chat with Georgios as well about some rheological stuff. But in the interests of time, I agree with you, Anya. We should maybe move on. But maybe another time, Georgios, we'll talk about these things. Is it time, Anya, to ask my question to Johan?
Yes, please. Thank you, Mike.
Okay. Johan, I think we've talked about bees before.
Yes.
So if I've followed your presentation well, the bees seem to be a surface phenomenon.
Yeah.
And okay, we don't really know about the bulk matrix of the material, but
we did some experiments on the bulk. So what we did, we had done this on both with AFM and with the Confoco. So what we did, we have frozen the bitumen to a very low temperature, and then we cracked it, and then we immediately looked at the surface, and we couldn't observe any bees at the surface. We also proved that if you have like a contact surface, so if there is a pressure on it, like water or glass, there is no way that they can start to wrinkle. So you need like a wrinkling effect. And if you restrict that by water or by a glass plate, it cannot happen. So that was one.
So my question is then, it's generally understood that what we have is a dynamic equilibrium in bitumen. And when we use the blunt instrument of SARA analysis to reduce the thousands of different species down to 4, I would welcome your views on so you took a bitumen which was in an equilibrium and did not exhibit these surface phenomena, and then you add in to that equilibrium some long chain paraffins, and then suddenly we see that they don't stay in the bitumen. So how do you interpret what is actually happening in the bulk matrix when we add something which was not there in the first place, and then we observe a phenomenon on the surface? How do you interpret what is happening in the equilibrium there?
Yeah, what we can see if we did the experiment with oil, because that was, it was an eye-opener, because we could look at what is happening in the bulb. Because if you take bitumen, the strength of the laser and the optical measurements, you cannot penetrate deep enough. You cannot see anything. But in the oil, we could see through the oil, and we could see that these particles, at a certain moment, they start to move, and they move up to the surface, and then you can see that this wrinkling effect starts to happen. What we are doing now is we are heating and cooling, and then we can see what is happening. So we can couple this to, for instance, DSC measurements, and we can see if we can see relations between the crystallization and the melting of the wax, so that we try to understand what is really happening with the wax and how it's affecting the surface. And I think it's a difference in surface in densities, or in you have different layers on top. So you have a contact layer, and then you have the wax. So there is a differences in surface tension or so, and that starts. There is a publication. I forgot it, but nevertheless, there is a difference in the tension, the surface tension, and then you can see, because when it starts, you see like a small dot, and then you see a certain propagation. And what we also see, if we need different lengths, because we need something where it can starts to propagate. If you have too small waxes, or the lengths are too small, you don't have points where they can start to propagate.
Thank you for that. In fact, I don't know if it could be related, but I think it may be worth looking at solubility parameters of these species.
That's what we are doing now, because when we heat and cool, we can sometimes see that some are not really soft. If you keep them for a long time, then they start to crystallize again. If you heat them up, you can see that some dissolve and some will not dissolve. So it's an equilibrium. But how to and understand what is happening. And the next step is of course, we want to couple this to adhesion, to stone, or to how it will react in a mortar, how it reacts on, for instance, a freezing thawing cycle, or what is the boiling water test, so the affinity to stones. How can these phenomena, because sometimes you have like a small gap between the bitumen and the stone surface. So what is the interaction between it? If it's a contact, or so I think it's very important to also understand the failure mechanisms in an asphalt matrix.
Well, I think also it may be worth your group looking at some work which I think was done by I think it was University of Austin, Texas. It's Amit Bassin's group. Anyway.
Yeah, I know.
They brought in some ants rather than bees.
Yeah, we see the same.
I don't want to be rude, gentlemen. Sorry about this. Now, this is a difficult situation for me. I wanted to inform you that a couple of participants already had to leave. This is very interesting to discuss, and that's one of the main aims we had with this webinar. And now I need to be the rude person to interrupt. I'm extremely sorry about this. It won't be lost, but definitely a lesson learned is that 45 minutes or 40 minutes foreseen for discussion might not be enough. So we will do that better next time. I would like to suggest that we come back to the topic separately and offline. So whoever would be interested to continue this discussion, please let me know, and I will coordinate with Johan about that. Thank you very much to everybody, but I would like, and I need to hand over to Vicente now, which I do with pleasure, but, and I'm sorry, I don't want to be rude, but I have to be.
Yeah, well, thank you very much, Anya. Thank you, being Georgios and Johan, for sharing your knowledge. In fact, it's been a pleasure having you here. And we are sorry that at the end we were starting to have a debate, and we need to close. But well, it's been a pleasure. Congratulations again for all the people involved in the research that you're doing. I think as Anya mentioned, all questions maybe you could be directed to via Anya to you if anyone in the audience is not want to make another question. So thank you so much, and thank you all the participants for joining and for your inputs. I believe it's been a great spread of knowledge, which is another one of our targets for these sessions. And well, that's all for today. So see you on next EUB3575 Academy sessions. Goodbye and have a nice day.
Thank you all. Bye bye.
Thank you very much. Bye bye.
Thank you all.
Bye bye. Thank you.
Goodbye.
Thank you. Bye.
Thanks. Bye.